Welcome to Chapter 6, Data Compression. Picture a screen filled with one solid color, a million pixels, but almost no information because every pixel is the same. Instead of storing a million copies, you store the color once and a count. A megabyte just shrank to a single line. In this chapter, you will learn how to make data smaller without losing anything, using run-length encoding, Huffman coding, and dictionary methods like LZ77. Picture a screen filled with one solid color. That is a million pixels, but it carries almost no information because every pixel is the same. So instead of storing a million copies, you store the color once and a count of how many times it repeats. A megabyte just shrank to a single short line. That is the whole idea of compression. Describe the same data with fewer bits, by spending bits only where the data actually changes. And in this chapter, the data stays exact. It usually goes out smaller, and it always comes back identical, bit for bit. Let's look at the plan for this video. It has 4 parts. First, why compress at all? The idea of redundancy and the important split between lossless and lossy compression. Second, run-length encoding, the simplest scheme, which collapses a run of repeats into a count times a symbol. Third, Huffman coding, the centerpiece, which gives short codes to frequent symbols and builds its code tree from the bottom up. And fourth, beyond Huffman, dictionary compression, and the LZ77 sliding window that points back to text it has already seen. Let's start with the reason compression is even possible. Real data repeats itself. Compression works because real data is redundant. Redundancy means predictable structure, repeats, patterns, or values you could have guessed from the ones around them. The more redundancy a file has, the more you can cut. It shows up in 3 main forms. First, repeated bytes, like a long run of the same pixel color. Second, skewed frequencies, where some symbols appear far more often than others. Third, repeated substrings, like a word that shows up again and again in a document. Now the flip side, and it is a real limit. Data with no redundancy at all, truly random bytes, cannot reliably be made smaller. Compression trades on structure, and random data has none to trade. So no method shrinks every possible input. All compression falls into one of 2 families, and the difference matters. Lossless compression gives back output that is identical to the original, bit for bit. Nothing is lost. When you unzip a file, you get the exact original back. ZIP, PNG, and FLAC are all lossless. Lossy compression permanently throws some detail away, so the output only approximates the original. JPEG photos, MP3 audio, and H.264 video are all lossy. Lossy can reach much smaller sizes precisely because it is allowed to discard information the eye or ear will barely miss. Everything in this chapter is lossless, so every method we build restores the original exactly. Now the simplest compression scheme there is. It attacks one kind of redundancy, consecutive repeats. Run-length encoding attacks consecutive repeats. A run is a stretch of the same value repeated back to back. Look at the input in the figure. The first run is X 3 times. Then Y 3 times. Then Z 5 times. And X again 3 times. That is 14 characters in all, but only 4 runs. The blue numbers count each run, and each run will become 1 count time symbol pair. How many in which symbol? Let's encode it, 1 run at a time. The first run is 3x's, which becomes the pair 3x. The next run is 3y's, the pair 3y. Then 5z's become 5z. And the last run, 3x's becomes 3x again. Write those pairs out as a string and you get 3x, 3y, 5z, 3x, which is 8 characters. So 14 characters became 8. 14 divided by 8 is 1.75, so the encoded form is 1.75 times smaller. Every one of those runs was long enough that 2 symbols beat spelling it out. Run length encoding only wins when the runs are long. Hand it data with no repeats and it backfires. Take the 6 letters A, B, C, D, E, F, 6 characters, no repeats. Each letter stands alone, so every run has length 1. Encoding puts a count of 1 in front of every single letter, giving 1A, 1B, 1C, 1D, 1E, 1F. That is 12 characters from an original 6. The data doubled. So run length encoding is not a general shrinker. It helps on long runs like solid regions of an image, and it hurts on data that does not repeat. Being honest about that limit is the point. Most data does not come in long runs. Huffman coding attacks a different kind of redundancy. Some symbols are simply more common than others. Huffman coding starts by counting. Take the message abracadabra. It is 11 symbols long, but only 5 distinct letters appear. The letter A appears 5 times. B appears twice. R appears twice. C appears once. And D appears once. Add those up and you get 11, which checks out. Notice how uneven the counts are. A lome is nearly half the message, while C and D appear just once each. That imbalance is exactly the redundancy Huffman will exploit. A fixed-length code like plain ASCII spends the same number of bits on every symbol, whether it appears once or 1,000 times. That is wasteful when the counts are uneven. An efficient variable-length code like Huffman gives frequent symbols short code words and rare symbols long ones. Since the frequent symbols dominate the message, the average code word length drops and the message gets smaller. So the frequent A should earn the shortest code, while the rare C and D can afford the longest. The question is how to pick those codes so the decoder is never confused. Huffman's tree answers it. Huffman builds the code with one simple rule. Start with every symbol as a lone leaf, labeled with its frequency. Then repeat one step. Take the 2 smallest available nodes and merge them into a new parent, whose value is the sum of the 2. That parent goes back into the pool. Keep merging until a single node is left, the root. The tree grows from the bottom up, and the rarest symbols merged first end up deepest, which is exactly why they get the longest codes. Let's watch it happen, one merge at a time. Merge 1, scan the leaves for the 2 smallest. C has frequency 1. And D has frequency 1. Those are the 2 smallest. Merge them into a new parent whose value is 1 plus 1, which is 2. Badge 1 marks this first merge. The old C and D are now children of that node, and the node of value 2 goes back into the pool to be merged later. Merge 2. Look at what is available now. I add 5, B at 2, R at 2, and the new node worth 2 from the last merge. The 2 smallest are R worth 2. And that merged node also worth 2. Join them into a parent worth 2 plus 2, which is 4. Badge 2 marks it. Ties are fine. Any two smallest will do, and this figure picks R and the previous merge. Merge 3. Now the pool holds at 5, B at 2, and the node worth 4. The two smallest are B, worth 2, and that node worth 4. Merge them into a parent worth 2 plus 4, which is 6. Badge 3 marks it. Only two nodes are left now, at 5 and this new node at 6. Merge 4, the last one. Two nodes remain, A worth 5, and the node worth 6. Merge them into a parent worth 5 plus 6, which is 11. That 11 is the total number of symbols in the message, so this node is the root, and the tree is complete. Badge 4 marks it. From one lone leaf per symbol, 4 merges built the whole tree. Now read the codes off the finished tree. Start at the root and walk down to each leaf, writing 0 for every left step and 1 for every right step. The frequent A sits one step away, so its code is just 0. B is 2 steps down, code 10. R is 3 steps down, code 110. And the rare C is 4 steps down, code 1110. And D is 4 steps down too, code 1111. Notice the pattern. The more frequent the symbol, the shorter its code. That is Huffman doing exactly what we wanted. Let's count the saving. A fixed-length code needs 3 bits per symbol, because 3 bits cover 5 distinct symbols. 11 symbols times 3 bits is 33 bits. Now Huffman, symbol by symbol. A uses a 1-bit code 5 times, that is 5 bits. B uses a 2-bit code twice, 4 bits. R uses a 3-bit code twice, 6 bits. And C and D each use a 4-bit code once, 8 bits together. Add them, 5 plus 4 plus 6 plus 8 is 23 bits. So 33 bits drop to 23, about 30% smaller, and the decompressed message is still exactly abracadabra. One more thing the tree gives you for free. Every symbol sits at a leaf, never on the path to another. That means no code word is the beginning of another code word. This is called the prefix-free property. Because of it, the decoder can read the bit stream left to right and know the instant a code word ends. The moment the bits match a leaf, that is the symbol, with no ambiguity. So Huffman needs no commas or markers between codes. The variable lengths cost nothing to separate. That is why prefix-free codes are the heart of real compressors. Huffman shortens single symbols by frequency, but a lot of redundancy lives in repeated phrases, not single symbols. The last family goes after those. Dictionary compression works on repeated phrases. Look at the string ABC, A, B, C, X, Y, Z, instead of storing a repeated substring again. It stores a short reference that points back to where that substring first appeared. The ABC at the start appears a second time, right after it. Rather than send those 3 letters twice, the encoder sends the second ABC as a pointer that says, "Copy the 3 letters you saw a moment ago." The dictionary is simply the text already sent, and a repeat that sits within that window and is long enough to be worth a reference can become a compact pointer. The classic dictionary method is LZ77, and it uses a sliding window with 2 parts. The search buffer holds the bytes already sent. In the figure, that is the first ABC. The look-ahead buffer holds the bytes still to come. Here a BCXYZ. At each step, the encoder searches the search buffer for the longest run of bytes that matches the start of the look-ahead. As bytes are encoded, the whole window slides forward, so the dictionary is always the recent past. That is where the name sliding window comes from. Now the match. The look ahead starts with a BC, and that same ABC sits 3 positions back in the search buffer. So the encoder emits a back reference, the token distance 3, length 3. The first 3 is the distance, go back 3 bytes. The second 3 is the length, copy 3 bytes from there. That one token replaces 3 literal characters. The output stream becomes A, B, C, then the token, then X, Y. Z, the repeated A, B, C became a single back reference token. Here the saving is slight because the repeat is short. The real win comes when a match is long, because one short token can stand in for a long repeat. On real text with long and frequent repeats, that saving grows large. The methods in this chapter are not rivals. The best compressors stack them. The most widely used example is deflate, which lives inside ZIP archives, gzip files, and PNG images. Deflate runs LZ77 first, replacing repeated substrings with back references. Then it runs Huffman Coding on what remains, the literals, the distances, and the lengths, giving short codes to whatever is now most frequent. Dictionary compression catches the repeated phrases, and Huffman squeezes the leftovers. Together they do far better than either alone. Let's gather what this chapter gave you. 4 takeaways from this chapter. First, compression trades on redundancy. It spends fewer bits where the data repeats. Truly random data cannot be shrunk, and lossless methods restore the original exactly, while lossy ones only approximate it. Second, run length encoding collapses a run into a count times a symbol. It wins big on long runs, but it expands data that does not repeat. Third, Huffman Coding builds a tree from the bottom up, merging the 2 smallest nodes each time, and gives frequent symbols the shortest codes. Those codes are prefix-free, so they decode with no separators. For Abracadabra, it took 33 bits down to 23. Fourth, dictionary compression, like LZ77, replaces a repeated substring with a back reference of distance and length. Real formats like deflate combine LZ77 with Huffman. That is Chapter 6. You can now spot redundancy in data, encode a run by hand with run length encoding, build a Huffman tree and read its prefix-free codes, and replace a repeat with an LZ77 back reference. This whole chapter was about removing redundancy to save space. Chapter 7 turns that idea around. To survive noise on a wire or a scratch on a disk, we will add redundancy back on purpose. Parity bits, checksums, and error-correcting codes that let a message detect and even repair its own damage. See you there.